In this video, I'd like to show you how I develop simulation and how I've developed the simulation for our particular robot. This is code that I'd like you to have, so I will create a new folder in your the code repository for this class and just call it simulation. As I mentioned in the assignment itself, I don't really have a preference for the language that you use, so I will just do mine in Python. And I'm going to do the position control. The position control assignment. So we'll step through that whole process. It won't have the sensor fusion in it. That's not going to be needed for simulating the path planning algorithms. It would be helpful for that, so feel free to put it in, but not strictly necessary. So I'll try to keep this simpler and just have us simulating position control only. And then you can take what I have here and build off of it and implement path planning on top of position control. I will almost always start by giving myself an easy way to sort of do a quick development cycle. I'm going to use Python to run my code. And this is normally the shebang you would use to run your default Python interpreter. I'm going to use a specific interpreter though. I'm going to use Anaconda, and I have a environment called Visualize that has a few extras that I'd like to use installed inside of it. So I'll just use the full path to the specific interpreter that I actually want to use in this case. This is something you'd want to change in your code. So for that reason, I'll add the line that you probably want to replace this one with. And I'm a pretty visual person, particularly when it comes to simulation, so I'm going to start by just having a plot pop up every time I run this code. And I think that's all I'll need to have a simple plot pop up. I need to navigate into the simulation directory. And this ran, there were no errors, no plot came up, and that's because when I run this as a script, I will need to say plt.show. And then off screen, this little pop-up comes up. And since that defaults to popping up off screen, you won't see it every time, but every time I save the file, this little thing will come up after I show you a quick little trick here. And that trick is to use a program. There are a lot of different versions of this. I happen to use one called watch exec, which will watch the files in the current directory, and I specified only watching the Python files in the current directory. And if any of those change, it will run Python position control. And this is why I put the full shebang here to my specific interpreter. That's because if I run it like this, it will use the version of Python that's not inside my Visualize environment. Instead, it'll use let's see, I guess a different one. I would have thought a different one would have showed up if I didn't have this environment activated. So I'm not entirely sure which one it's using actually if I don't have it, if I don't have the environment activated. In any case, I can make a couple changes to this. What I'd like to be able to do is run my program like this so that the operating system, actually the shell, uses this specific interpreter. And I can do that by giving the execute permission, or adding the execute permission to this file. And so that'll run. I get my pop-up. And now I can change this one to run the program like so. I'll run it, I'll get my pop-up, I can close it, and now this is actually technically still running. And if I modify something in the file, and save the file, it'll automatically rerun and plot and show the plot. So now I can have a quick cycle of making changes to my code, saving the file, and then automatically having the updated plot plotted. Alright, after a bit of trial and error, I found if I add this magical line of code along with this one, if I save the file, the figure will pop up in range here, so I don't have to keep dragging it over in range. Alright, so for the goal of this simulation is for us to find appropriate values for x and y, such that when we plot it, we're showing position control. So almost always I'll start a simulation by having a time variable, and I'll almost always also have a time step variable. And out of habit, I'll just start that at 0.1, and I can increase or decrease that depending on the results that I'm getting, if they make sense or not. And if they make sense or not is a bit of an intuition that you'll have to build. We'll also have a duration, so how long do we want our simulation to run? And that's enough code that it's probably worth running this to see what we're getting for results. So I'll have a while loop, and I can say while time is less than my duration, and inside here I need to increment my time step, and let's just arbitrarily say that x is going to be some value for time, and for y's, let's just say it's time times 2, just so that x and y's have the same number of elements. I can save it and plot it. Depending on how complicated this code gets, I might want to wrap this entire function, all of these values inside of a function. So normally I would start collecting my constants near the top of the file, because eventually I would make these program arguments so that I could run a variety of different values without having to actually edit my code. And then I can have a function here called simulate, which does our actual simulation. And we can return our position values so that they can be plotted outside. So just following sort of standard Python idioms, normally I would have a main function. Inside here I could define an argument parser. I could pass in one of my arguments, which is duration. And then after that I can have my plots. And currently when I save this, you'll notice it says it ran successfully, but nothing actually happened. And that's because I'm not actually calling my main function. Right. Is that the syntax for it? Well, saving it didn't get anything to run. This is one of those places where Copilot is actually going to be useful. So let's enable it, give it a prompt, and that's what I was looking for. Okay. Now when we run it, we get this sort of nonsense plot. And now we can do something useful inside of our loop here, our actual numerical simulation. This will end up looking pretty similar to what we had in the slides. And for position control, that looks something like first performing forward kinematics, and then performing our position control update. And I pretty much always pass in, like I've done here, those global variables. Even though they're accessible everywhere, I like to pass them in so that they just show up in one place, basically just down here in the main function. So to help me remember that, I am going to move those here. And now I'll get some nice linting errors telling me when things are not defined. So this now is lowercase duration. This will be lowercase time step, lowercase goal threshold. Alright, and so now the only things not defined are my actual kinematics and forward, or position control. But before I do that, I'll also mention I'm a big fan of Python type hints. So my duration will be a float, same with my time step, and same with my goal threshold. And instead of returning values that are x's and y's, let's define a new type here called a pose. And I'm just going to copy that over from my working code. So here's a pose. It's going to have an x value, a y value, and a theta. And if I don't want to, which I don't, have to create the constructor that initializes x, y, and theta, basically the same constructor that you'd almost always write, I can use this data class decorator. Which just means that those automatically get defined for me. So this data class will automatically have that sort of useful version of a constructor defined for me so that I can do something like pose with a value for x, a value for y, and a value for theta without having to do it manually. And so that's really what simulation will return, is a list of poses. And now I should be getting a complaint here, but I'm not yet, and that's probably because it hasn't gotten that far in code. The linter, that is. It's still confused by my missing forward kinematics and position control. So let's just focus on forward kinematics for now. All forward kinematics needs to do is take the current velocities and step us forward through time, so basically taking our current pose and moving us. And since forward kinematics is something we've discussed earlier in the semester, I'm going to copy that over as well. So here's my forward kinematics object. It does have a more complex constructor, meaning I can't just declare this one as a data class. It'll have an initial pose at 0, 0, 0. It'll have an update function that takes velocities and returns a pose. And from the time that I wrote this to now, I think I would rather call this v, the velocity. And I still like theta dot for the name of this one. But maybe it would be easier to read if I did theta dot, which is what that little squiggly was indicating, is it was a difficult to read variable. They weren't actual words. And I really should have used the renaming utility so that it renamed it in all places. Cosine and sine are not defined, but I can automatically import them. And wrapped pi is a utility that I often use. I'm just going to copy that one over. Essentially, it makes sure that the value you get from whatever sort of computation you're doing on an angle is constrained to negative pi to pi. And pi needs to be imported as well. So those get automatically imported when I click on that little pop-up. Now my last complaint here from the linter is that I've never actually created the forward kinematics object. And I need to give it a track width, so we can add that to a list of our parameters. And I typically like to use put these in order of use or in order of type. So we'll have our time parameters and then our kinematics parameters next. Now the air has been pushed down. Well, should have been pushed down to here, because I haven't actually passed that into simulate. Simulate now requires a duration, a time step, a track width, and a goal threshold. Let's say if you're within 10 centimeters of the target, you're close enough. Alright, now I've not defined the actual velocities. Now I should be at the point where if I run this, I'll get another plot popping up. And nothing. What's the error this time? I'm actually surprised the linter is not catching that. I'm now getting poses from simulate, which means I need to extract the values for x and y. I'm just going to be lazy and do this as two separate list comprehensions. And now this is running and I'm getting our pop-up. There's nothing in that data because it's returning an empty list. And now, assuming that my forward kinematics actually works, we can actually get this to run forward. So let's just arbitrarily give it a lot of speed, actually. So this will run pretty quickly. So we have poses. And I think all we need to do is make those changes. And we're not getting anything when we run it. So here's where having the automatic running comes in handy as well. So why am I not getting anything? I could fire up the debugger, or I could just see what am I getting inside x's when I run this. Alright, those all look like pretty reasonable values, although they're all the same value, which is not quite what I would expect. And am I getting something similar for the y's? Can't tell if that reran. Ah, it won't rerun because I need to kill the figure for that process to complete. Okay, those are all always the same value, but again, not the same as the previous value. I have a suspicion here that since it's always the same value, this is always a reference, meaning even though I have multiple copies of that reference, they all point to the exact same space in memory. If I call copy, this will probably say that doesn't exist. But what I should probably do is just add that functionality. There is a way to make that annotation work. What is that? Maybe that's what it is. No? Alright, a bit of looking at the documentation, and what I was missing was this line. From future import annotations, and then Python's happy to use this sort of syntax where I can return pose, even though pose isn't technically defined until after the class is defined fully. And of course, since this package can impact others, they want it imported at the beginning. Alright, and since we set this thing to have the right wheel a little bit faster, this thing is turning off to the left. One thing that's really important is to make sure that your axes are equal, and I can't quite tell if that looks reasonably equal or if I'm getting a weird distorted view. So let's go down to our plot. And I never remember how to do this. Is it just equal? No, it did not like that. And the correct invocation there is to call it on the axis, not plot itself. So you get the current axis, set it to equal, and my auto formatter is not on, so I'm getting mixes of single quotes and double quotes. That's going to annoy me. Alright, we no longer need this print. Now what's left to do in our simulation is to update this and have it go to a specific goal. So now we need a position control object, and I'll copy that over from my existing code as well. Alright, that's copied over. Let's see if I still like the way I named variables, and I don't think I did. I try to get into a good habit of, whenever I have variables that have the same attribute in different names, putting the attribute first. It's not always as natural to read, but it does mean things line up a little bit nicer. So, for example, I'll change this one, and you can see like the velocities are not aligned, and it's a little bit harder to read because of that. But if I were to name this one max velocity in the angular case, and rename this one max velocity in the linear case, you'll see that these variables line up a little bit more nicely. And, I have to change it here too because that's a different variable since it's on self. I'll do a little bit cleaning up of the variable names here, and then I'll resume the video. So a slight improvement here on how well these two things line up. Slightly better for readability. Alright, and then what do I have for the update function? Returns to floats. Those will be the velocities. And I noticed this in some of URL code that I'll steal because I think it makes the code a little bit more readable. So that shows up in these two places. So let's call that dx. And we'll call that one dy. Oh no, I was changing code in two places. Alright, so our distance error, dx times dx plus dx times, dy times dy, take the square root. If it's less than the threshold, which is passed in here, return zeros. And then my linear velocity component is based on my gain for position and then my position error. And that's always going to be a positive value. D error, the square root, will always be a positive value. So I don't have to worry about constraining that on the negative side. A tan 2 needs to be imported. And this time I don't have quite the same guarantee. The error on theta is not guaranteed to be positive. So currently I'm just checking the upper bound, and I should really be checking both the upper bound and the lower bound. So that was an error in my code, and I probably put it that way in previous videos, and I saw it in many of your code too, which is that we're only checking on the min side. So let's also check that on the upper side. So I want the maximum between theta dot and a negative of the constraint. So basically I'm capping on the max side and then a lower end cap on the negative side. Computing values for left velocity and right velocity and returning them. And now I just need to create that position control object. It requires a goal for the x and the y, a max angular velocity, a max linear velocity, a track width, a gain for the orientation, a gain for the position controller, and that appears to be it. And this is where I really miss having my auto formatter set up. That's probably reasonable formatting, if not conventional. Now I'll spare you the details of having me copy over constants for all of these and then adding them to this function. I'll just show you the end result here. Alright, so I've now copied over all of my constants and added them to the simulate function. Those are the only two changes I've made. And then this code looks a little bit gnarly now. And saving it, and it looks like we're getting something fairly reasonable here. Starting about 0, 0. I'm not sure why we're quite so far off from the actual 0 here. Probably taking at least one step before we've actually moved. And then heading toward, it looks like I set the goal to -1, 1. So all that looks pretty reasonable. Let's add that initial pose. So if I save that one, yeah, okay, so now I'm starting at exactly 0, 0. And it would be worth putting my goal position let's see, I believe the syntax for that is they both have to come in lists, something like that. I don't know if I'm getting a point there. What if I ask it to have a circle at it? Okay, so now I'm at a circle, and am I within about a 1 centimeter radius from there? I say 1 centimeter because that's the goal threshold I put here. Let's change that to about half that distance and rerun it. It does not look any closer to me. Try to make that even smaller. No difference there. I'll do a quick bit of debugging here and see if there's anything there that I need to be worried about, or if I'm just missing something obvious. Looking around through my code a little bit, I didn't see anything obvious. I did notice that I still had these initialized to unreasonable values, but I'm wondering if it's the duration. Maybe 10 seconds isn't enough. Let's try 20. Okay, so that must have been what the problem was, is I just wasn't giving it enough time to actually get to the goal. So now if I adjust my goal threshold, put it back up to 10 centimeters, I'm getting to, it looks like 0.9, 0.97. And if I make that even larger, yeah, okay. So this now looks like it's functioning in about the way that I would expect. So the last part here that I would do if I were taking this to completion would be to turn all of these, maybe not all of them, but all of the relevant ones here into command line arguments. Definitely the goals and probably the goal threshold. Definitely the control parameters, but probably not the track width. I'm going to say that's probably just a fixed value that we would use. And actually now I'm noticing a conspicuous absence here of wheel radius. Do I have that just hard-coded in somewhere? And forward kinematics. No, that's right, because I'm just dealing with wheel velocities directly and not worrying about angular velocities of the wheels. And that probably means I need to rename some of my variables. No, okay. I understand what I was just thinking about incorrectly there. This actually is an angular velocity. It's just how fast the robot's allowed to rotate essentially in place. Think of it in terms of a 0-degree turning radius on the spot. How fast can that rotate? It's not the angular velocity of the wheels themselves. All right. So this code is in fact correct with that regard. All right. There's nothing else I'd like to show in this video, so I will end this here. Post this to both the chapter, and then I'll make sure to commit this to the repository so that you have access to it. Let me know if you have any questions on Slack. Thanks.